Title of the first section today is Simplify Square Roots. In this section, we'll simplify square roots or radicals. First equation is square root of 125. Simplifying a square root, there is no single number times itself that equals 125. So to simplify the square root, we can do a factor tree. With a factor tree, we'll pick two numbers that multiply to get 125. Two numbers that multiply to get 125 is 5 times 25. Continuing the factor tree, 5 cannot be factored anymore, but 25 we can factor. 25 would be 5 times 5. After the factor tree is fully complete and cannot be simplified anymore, a square root, we're looking for two numbers or pairs of numbers. We can circle a pair of numbers like a pair of 5s, and any numbers you circle, your first answer would be 5. Any numbers that we did not circle as extra 5 will stay inside the square root. So our final answer would be 5 square root 5 or 5 radical 5. The 125 and 25 we don't use because we factored them. We only use the numbers at the bottom of the factor tree. And second question, last question for the section. We have the square root of a fraction, 350 divided by 81. Simplifying a square root with a fraction, we can take the square root of the top number or numerator and also the square root of the denominator. The first number, 350, we can take the square root of, again by doing a factor tree. You can pick any two numbers that multiply to get 350. If the number ends in a 0, we can use 10, 35 times 10. Factoring further, 35, two numbers that multiply, we can do 5 times 7. And two other numbers that multiply to get 10, we can do 5 times 2. Again, once you factor or do the factor tree, the square roots means we're looking for pairs or two numbers that multiply. We have one pair of 5s, which we can circle. If you circle a single pair of 5s, again, the number outside the square root would be 5. We have two numbers that we factored, or the prime factors that we did not circle, 7 and 2. Those will go inside the square root and we'll multiply them 7 times 2. For the denominator, square root of 81 would just be 9. So our answer would be 5 radical or square root of 14 and divided by 9. Title of the next section is Square Roots with negative numbers. In this section, we'll take square roots or radicals, but the number will be negative. First question is the square root of negative 1. There is no number times itself that equals negative 1. So a new definition that we use, or a new variable, letter I, will be an imaginary number. I will stand for the square root of negative 1. In other words, I times I would be negative 1. Second question, the square root of negative 144. And again, there is no real number times itself that equals negative 144. What we can do to solve this one is just take the number 144, the square root of 144 would be 12, and since it's negative 144, the answer will be 12i. So 12i times 12i would be negative 144. And last question for the section, the square root of negative 100, a to the fourth, b squared, and c. So the square root of negative 100, a to the fourth, b squared, and c. Simplifying this, again, negative 100 will be an imaginary number. The square root of 100 would be 10. And since it's a negative, we'll have 10i. Square root of a to the fourth. A to the fourth, if you want to, you can write out 4 a's. And similar to the factor tree, you can circle pairs since we're taking the square root. We have 2 pairs of a's, which means we'll have a squared. B squared, the square root of b squared. Likewise, you could write down 2 b's. There's 1 pair of b's, so the square root of b squared would be b. We have a single c, so there's no pairs for the c's, so the c will stay inside the square root. Rewriting our answer, we'll have the number first, 10. The variables a squared and b we'll put second. The letter I we'll put after the variables, and the square root c we'll leave inside the square root. So our final answer would be 10 a squared bi times the square root of c. Expressions with imaginary numbers. Using the following information, we'll be able to simplify questions that have imaginary numbers that also have exponents. The first one, I, is equal to the square root of negative 1. Any questions that have a single I, we can leave with I for imaginary numbers. Second one, I squared. I squared will be equal to negative 1. I squared, we're multiplying the square root of negative 1 times itself, which would equal negative 1. So any question with I squared, we can rewrite using a negative 1. I to the third power would be I times I squared, so that would be negative 1 times I, which would be negative I. Any questions that we have I to the third, we can rewrite with negative I. And the last one, I to the fourth. I to the fourth would be I squared times I squared, or negative 1 times negative 1, which would be positive 1. So any question was I to the fourth, we can rewrite using positive 1. Any questions with I to the fifth or greater, we can simplify I to the fifth to one of these smaller numbers and rewrite them. So all the questions will either have I with no exponent or one of the other numbers. First question for the section is I to the 14th power. Again, anytime you have an imaginary number to an exponent, we can simplify that. Easiest way to simplify exponents is to take the number 14 and we'll divide by 4 and find out what the remainder is. 4 will go into 14 3 times and we'll have 2 left over, so the remainder would be 2. If the remainder is 2, what that means is I to the 14th is equal to I to the second power. So if you have any number with an I as an exponent, we can divide by 4 and the remainder is the same as the original exponent. Looking back at the table, I squared is equal to negative 1. So our answer, I to the 14th, is equal to negative 1. Second question. First parentheses will have negative 2i. second parentheses, negative 6i, and times last parentheses 4 times I. I's are similar to variables. We can multiply them or combine like terms when possible. For this one, we can multiply the coefficients. Negative 2 times negative 6 would be 12. 12 times 4 would be 48. And we have I times I times I, which would be I to the third power. Simplifying, 48 would stay the same. I to the third power, looking back at the table that we just wrote, I to the third power is equal to negative I. And if we multiply 48 times negative I, that would be negative 48i. So simplifying the expression, the answer would be negative 48i. Next question for this section is 3 minus 4i minus a second parentheses 1 minus 4i. Again, i's for imaginary numbers are just like variables. You can combine like terms when possible. If we start with the 3 and combine it with the 1, 3 minus 1 would be 2. And we'll also have a negative 4i minus a negative 4i. For minusing a negative 4, it's the same thing as adding 4. Negative 4i plus 4i would be 0i. 0i we can leave off, so the answer would just be 2. Next question for this section. First parentheses, we have 3 plus 4i times a second parentheses 3 minus 4i. Multiplying imaginary numbers or multiplying i's, we can multiply them just like a normal variable. Two parentheses we can multiply or use FOIL. 3 times 3 would be 9, and the outside terms, 3 times a negative 4i would be negative 12i. Multiplying the inside terms, positive 4i times 3 would be positive 12i. And multiplying the last terms, 4i times a negative 4i, 4 times a negative 4 would be negative 16, and I times I would be I squared. Simplifying, the 9 would stay the same. Negative 12i plus 12i would equal 0 or cancel. And we'll have minus 16 instead of I squared. Looking back at the table, I squared is equal to negative 1. So we'll have 19. Negative 16 times negative 1 would be positive 16. And 9 plus 16 would be 25. So multiplying these two parentheses, the product is equal to 25. And last problem for the section is 3 plus 4i divided by 3 minus 4i. To simplify this, one rule with imaginary numbers, similar to exponents or radicals. If we have 3 minus 4i in the denominator, one rule is we cannot have imaginary numbers in the denominator. They're okay in the numerator, but if you have imaginary numbers in the denominator, we have to cancel that out. To cancel out the I in the denominator, if we have 3 minus 4i, we can multiply by the opposite or conjugate of that, which would be 3 plus 4i. If we multiply the denominator by 3 plus 4i, we'll multiply the numerator by the same 3 plus 4i. Multiplying the numerators, we can multiply using FOIL. 3 times 3 would be 9. 3 times 4i would be 12i. 4i times 3 would be 12i. And 4i times 4i would be 16i. Multiplying the denominators, 3 minus 4i and 3 plus 4i. That's the same as the previous question we just did, which was equal to 25. So for the denominator, 3 minus 4i times 3 plus 4i, same answer we had before, which is 25. Simplifying the fraction, 9 would stay the same. 12i plus 12i would be 24i. And the 16i was actually I times I, that would be I squared. And we'll have 16 I squared, looking back at the table, which is negative 1 over 25. Combine like terms again. We'll have 16 times negative 1, which will be negative 16. 9 minus 16 would be negative 7, plus 24i divided by 25. So our answer to the question, negative 7 plus 24i divided by 25.